I wanted to just kind of kick us off thinking about the concept of doing many things at once. And this gentleman certainly is doing that. The interesting thing when the poll question came up was how many of you are grinding serious geometric processing. And the multiprocessing capabilities in FME, I think, can definitely play a key role in reducing the time it takes to do those sorts of things. So just to kind of introduce it, multiprocessing is the idea that you're going to use more than one of your CPUs to do something. And in the old days when we started, we were lucky to have even one CPU in a computer. Today, even your wimpiest MacBook Air consumer-grade computer will have at least 4. So a desktop's often 8 to 16. So it seems a shame not to make use of them. And so we do have some threading in FME data through in a shorter time. And to give you a bit of an idea of the kind of benefits you get, and the key thing that I do not have a slide to say, but whenever you're thinking about using multiprocessing, there's a trade-off. Just like almost everything that you do with FME, there are pluses and minuses that you have to keep in mind. And so really, a great FME user is as much an artist as a scientist, perhaps. But the multiprocessing trade-off is this. To use multiprocessing, we have to send data to different processes. There's a transport cost to moving the data. Once we get it moved, now we're going to do the processing. For multiprocessing to really give you a benefit, the amount of effort in the processing has to greatly exceed the amount of effort to transport the data around. So we shouldn't do multiprocessing so we can do a scale of the data or an offset, because that's just too little work in comparison to the effort of moving the data around. On the other hand, if we're doing 3D clipping of point clouds, that's a lot of work for each point to figure out if it's in a certain cube or something like that. Or buffering is a great example. Dissolving is another fantastic example as well, where the amount of CPU we're doing on each object is great compared to the time it takes to send it around. Many raster operations also fit into that category. So how do we turn it on? Well, there's a setting on transformers, on many of them, that lets you turn on parallel processing. And how does it work? Well, you have to have specified a group. And so basically, for each group in the group by, we will then spin up a different process to handle those groups independently. And that's basically the concept. Now, we give you some colloquially named terms about how much or how little you'd like to do parallel processing, and you might ask, well, why would you have these settings? In some cases, the amount of work you're going to do in each process is so large and requires so much memory that you don't want these processes fighting each other. So this is where minimal or moderate may be in order. So in other words, the amount of memory that each thing is going to take is actually very large. And so we don't want, since the computer may have finite amounts of memory, we don't want to be bumping into each other. On the other hand, you may be doing things that do not require much memory. And one example is I want to do a bunch of web service calls where each process is going to make 3,000 web service calls, but mostly we're just waiting on the network. So in that case, we might as well go for extreme and have many of these hitting the network at once, and we should get done quicker. One other thing to really keep in mind is that any custom transformer you make can be invoked as in parallel processing. So in other words, if you know that you're going to do a dissolve and then an area calculation and then a sort to pick out the largest thing, that would be great to put all those 3 things into one custom transformer and then parallel process on that. In general, because again the cost is in sending the data, you want to do as much work once you've sent the data. So if you have a stream of things that are independent that can work on a chunk of data independent from any others, string those together, do as much as you can, do that all separately, and then when you are done, bring it back together, and you'll have a good result. Now, again, on these levels, we tried to make up these names, but here's how they really translate into reality. There's 2 things, and kind of like the NHL, we have a salary cap or a process cap based on your license level, but we never go on strike. We always do our job.
Dale, I don't know if everyone's going to get that reference.
Well, there's going to be at least 3 or 4 Canadians who are bitter that way. NHL is on strike, so all the people in North America can do is play with FME in the off hours to entertain themselves. But anyway, there is a cap. If you have a base level license, the most we're going to let you do is 4 processes. Professional is 8, and everything else will let you do 16. And Mark Ireland did ask me a tough question, and I did not get the answer. If you use the workspace runner, we do let you get all the way to 32, and I guess we say, you know what, if you're using the workspace runner, good on you. You can do 16 more. I don't know why that is the case, and I will look into that. But
I'd like a little image there, the levels that are parallel.
Yes, exactly. I wonder who made that image, Mark. I wonder who it was. Yes, it was Mark Ireland himself. But it is very, I didn't actually notice that those were levels, to tell you the truth, until right now. I thought they were chips before, but yes, they are levels.
Levels of parallel.
That's right, parallel levels. So anyway, if you set it to no parallelism, of course we do just 1, and then it's a function of the number of cores. So extreme will say if you have a 4-core machine, we'll go double that, and that would give us 8. So we would not hit the salary cap if we were a professional. So that's how that math is done. So just in summary, before we look at an example, and I know we are getting dangerously close to 12, 12, 12, 12 in the East Coast, so we want to stop well before that. The main thing I'd like to point out is a great article that Mark did, The Evangelist 94. And Ken, you are going to make these slides available afterwards, right?
Yeah, slides and workspaces will be on safe.com. The link's on the last slide. Yep.
So that's great. So you can look at that later. And also, Dimitri did a really good write-up on FMEpedia, which with luck I will flip to here. And he goes through a number of different scenarios looking at the impact that parallel processing can have. So making DEMs, and you can see, here's some of the examples. And again, we're doing this with smaller data volumes. Those of you with very large data volumes will see even more dramatic savings. If we're cutting it in half here, that's 30 seconds, but that's no big deal. But if it's in half and it's 2 days, I can make a Scotty reference. If it goes by the book, days could turn into hours, and then that would be very good. Here's an interesting example where you actually chain something, and those of you that know about the Google technique of map reduce, where you throw out a bunch of work to be done, and then you bring it all back together, and you do a little last bit of work to reduce those answers to 1. In this case, Dimitri made a tin for every input LiDAR thing, and then he gets those were done in parallel, and then the results he brings back and makes into just 1 tin at the end. And if I have time, I'll try to make up a dissolve example that would be like that. Dissolve a bunch of pieces into bigger pieces and then gather them together and do the final dissolve here. That's a typical type of technique, and you can see this thing goes from 5 minutes down to 30 seconds, and that does give us those Scotty type answers that we're looking for. So in my last couple minutes, I'll just look at this example where I won't run this one because it takes 1:36. What we do is we are doing the shortest path from, this is a network of the Vancouver streets, and we're reading 500 of our properties, adding the location of the Vancouver General Hospital. So we've got a from-to line from the property to the hospital, routing those into the shortest path finder and saying, hey, find me the shortest path. Well, in some respects, every one of these could be done separately. So I'll just show how I would start to do this. I would have to divide these properties into different groups, and so this is sort of the trick. One of the tricks is multiprocessing. And to do that, I'd throw down a modulo counter, and let's just say I would do it with 3 groups. I'm going to make 3 different groups. Whoops, and I should name the output underscore group. So I've got 3 groups going. Now I would tell the shortest path finder, hey, group this thing by group. That's fantastic. Crank her to, let's go extreme. Just for, well, that probably would be a bad choice unless I have lots of memory. Maybe moderate would be good. And now I'd be good, except you'd say to me, well, Dale, you divided all you got to be careful when you're doing this when there's multiple input ports. If I was dissolving, I'd be done. But here I got 2 input ports. I've made a nice group on the guys that I know that I'm interested in that have to be different, the from-to nodes. But what about the network? It doesn't have a group. And so here, I sadly enough have to clone the network. And I'm going to make 3 copies, one for every group, and I'll name them 0, 1, 2, 3 will go into this as well, and that would do the trick. So just to prove that that works, and I'll just open up my other example here. And this is exactly that. I've named it a bit better, and this will be the one you get. Divide into groups as a modulo counter, copy per group. And what I did here, just to make sure I don't goof up, is I assigned a private parameter to both of these things so that my number of groups stays in sync. And now I'll go ahead and run this, and nothing's quite as exciting as watching a parallel processing thing run. You can see all the different log pieces rolling by with their prefix. Here I'm paying a bit of a price because I'm sending 17,000 features times 3 into every group. And I'm only doing a measly 167 or so bits of actual work in every group. Now if I would do every address in Vancouver, I would see even a more dramatic speed up than what I'm going to see here. This thing is going to end up taking about 50 seconds down from 136, and that's even with the huge overhead I've got of all those clones. So that's that one, and probably the other thing I was going to show, which I won't get into, but this is an example of a tax lot thing where I might want to do a dissolve. So I could do a dissolver here, and then I would do something ahead of time to assign. I wouldn't actually do, whoops, okay, there must come my shortest paths are done. And so let's just turn off the network. Yeah, these are all the shortest paths for these people that need to get to VGH. And so let me just flip back. And it took 59 seconds because I was fiddling around, but still down from 1:36, worth it for this particular case. Hopping back to my dissolve case, I'd have to figure out a clever way to partition the input. And this is not a clever way. By assigning a number from 1 to 3 to everything coming in is probably not a good thing because I would get random things. I would rather basically do a feature count and do a divide by 1,000 or something to get me different groups. Then dissolve by those groups. That would give me 20 things out. And then lastly, I would do one more dissolver at the very end to catch and dissolve that. And that would be a much improved thing. And I will actually make that example to give to Ken to include in the output or in the slides.